There we go. Okay. So thank you, Wolfgang. So I am from Here Technologies. We're a global maps company. Google is one of our competitors. I work on the search team, and we have this is work related to some of the sort of machine learning models. It's like a feature engineering thing. And just for background, not to advertise or something, we have several services that we provide. A geocoding service and search. You go to like wegohere.com and you type in addresses or place names or whatever, and so we have that. We have logs. All of these sort of requests sort of log, and from the geocoder side, we also have. Well, just for background, geocoding is you put in sort of a human understandable place location, you get a coordinate, a latitude and a longitude, and we have a service that goes the other way too. So all this data gets logged. And so we have a lot of coordinates. And so what you can do is you can do some kind of cellulation or tiling of the Earth, and you can aggregate. And what you end up with is a very sort of like super resolution map. And because of our customers and where they are, it actually, you'll see it's quite striking. But that's kind of the background. And the genesis for this is our auto-completion service. Again, it's what you think it is. You type in some characters and you get some suggestions. And just to explain what auto-completion is, and maybe I don't have to explain it, but the idea is, the user wants to, avoid misspelling something. We've all tried, typing something into the query box, and we're like, have a rough idea of what we want, and auto-completion helps us get our answers. So these are the, sort of main reasons you want to have something like this. And so the reason we care about the human avalanche in our service is that we use it to rank those results. So it's we sort of use it as a signal to compute something like a place importance, we call it, and and the heat map is basically a distribution. So you can think of it that way. And I guess you can read. So again, we take the Earth and we sort of cellulate it, latitude, longitude, and we sum up the coordinates that we have in our logs and assign them to different tiles. And just so everybody knows, so latitude is a north-south bearing, and longitude is an east-west bearing, right? And so this would be a cell, not an accurate size, but that would be a cell in this data set. And so the idea is that if you have, coordinates here, 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 we kind of aggregate them to one sort of key, which would be in the lower left-hand corner. I think I have a picture of that, yeah. So I hand drew that. It took forever in GIMP. And so we cover this. The Earth is not flat. We know this. So each cell has a different area, and you can model the sphere in many ways. But the common sort of way to model it, or the simplest anyway, mathematically, is using a sphere. At least if you do that, you get closed formulas. And you could so I did this, I computed what the area would be, you do a double integral, and I just took samplings, and this is what you get. So this is Bangalore, south of Market, San Francisco, Frankfurt, Stockholm. And so you can see that near the equator, we're at 120 square meters, and here in Frankfurt, we're at like 80 or something. So there's 50% difference. There's quite a difference depending where you are on the Earth. So as I said, this isn't a typical sort of image, and one of the reasons it's not typical is it's not acquired by camera. It's also, you think of it as just having a luminance channel in grayscale, but it's not acquired by a camera. And it also has, it's like super resolution, yeah? So just for comparison, it's like 1,000,000 times or 7,000,000 times the resolution of like a 4K like television or something display. So what are the challenges with visualizing it? And you can imagine that with something as high resolution, you can raster, right? So you can take the resolution, the target resolution, and the base resolution, just like map to pixels. And so we can do this, and you're looking at nothing, right? But there's something there, and what you're seeing is that the image is like super low contrast, right? So it's you have after dividing by area, we have really low sort of values. We have some high values because this is like matplotlib, so it automatically kind of identified or sort of ranged the plot to like, I don't know, 5,400. They're there, but they're sort of hidden. So what we want to do is to sort of rescale the pixel values. Just to give you an idea of what's going on, so we have, this is the histogram of the image, and what you see is what looks like a highlighted axis, but what you're seeing actually here is data. This is what the histogram is. That's like how skewed it is. And just to get a closer look, we zoom in, and there you finally see some kind of something that looks like a distribution, right? It's like that. That's so first approach for people who've done this is what we'll see is just to take the log of the pixel values. But there's a principle behind this. So this isn't necessarily a famous blog or anything like that, but it's quite nice. This blog post by a guy from NASA. I don't think he's there now. He's at like Planet Labs or something like that. But anyway, he has this nice quote, and he says that computers calculate light linearly, but humans perceive light exponentially. And there's some experimental evidence and even studies that go back to the 19th century to verify this. So if you do some searching, you'll find these guys, these dudes, Ernst Weber and Gustav Fechner. And Weber did these like perception experiments with physical stimuli. Oh. That's a subtle signal. Thanks. So Weber was kind of like one of these amateur, maybe semi-professional scientists like you had in the 19th century, and he did kind of experiments on how people perceive like stimuli. So like weight, I give you a 100 kg weight, and how much more weight do I have to add so you feel it? You feel the difference, or you register a difference. And you can do the same thing for, I don't know, determining brightness and hearing and so forth. And so he took all these data down, did these experiments, and then he had a student who presumably was younger when they knew each other, who was a bit more sort of mathematical, a bit more modern maybe. And looking at the data, besides saying, oh, you have to, when the luminance level is higher or the weight is higher, you have to add more weight for somebody to notice, and he actually noticed a sort of formula. And here we note sort of change in perception, perception having units. Difference in perception is related to the ratio of change in this case, luminance, and change in luminance over the luminance level, the absolute level. And so what you can do is a little bit of math, and you can take these sort of differences and make them infinitesimal, and then integrate, and then you get a log. it's a nice sort of, I would say proof, but a sketch of how you justify using, taking the log of pixels. And so we can just, we can linearize perception by taking the log. So let's do that. And now you see something. So what do you see? You see a lot of red, but you also see a lot of black. This is the Frankfurt region. It's still low contrast though, yeah? And we're not occupying much of this range, but it would be nice if we could. In a sort of principled way, it'd be nice to stretch the contrast a bit. So this is satisfying, but we can do better. Okay. So there are two problems we tried to solve. One is visualization, the other, and the next one that we wanted to do, at least at the company, was comparison. And there's a solution to both. So it's okay. We have a kind of solution, solution, taking the log of pixels, fine. But what if we go ahead and try to do some sort of comparison? And well, this is actually based on our real data. We do different data sets. And we have here, I just picked two statistics about statistics about the image. We have data set 1, we had 6 billion requests. And the other, we had a third of that, so almost 2 billion requests. And then look, the counts are different. So it's like, okay, typically if I have 2 images, what I want to do is just subtract them or something, and then look at the difference. But what if I choose a different time frame? What do I do, right? So we need to normalize this amount, and with the log, you don't get that. So we need some sort of true normalization. So in comes our solution, which is histogram equalization. So people who, I guess, work in image processing or have signal processing backgrounds, maybe they know about this. So the idea here is, if you have like 2 sets of students, maybe we all went to universities somewhere. Universities have to, maybe they use tests, for instance, to compare students in different places. And those tests maybe have different scales or something, right? Maybe they use a 0 to 100 in one place and 0 to 1,000 in another place. So then how do you compare students? And the idea here is to compare by how you rank inside your cohort. So the example here is, on some of these state exams, at least when I was a kid, they'd say you were in the 90th percentile, the 80th percentile, or something like that. That's literally what we're going to do. We're going to take the pixel value, rank it against all the others in its cohort, in its data set, and then assign it this rank. And then multiply by a number, and that number will be whatever we choose. So in sort of, with regard to our histograms, what we're going to do, and this is sort of a heuristic diagram, it's not meant to be literal, we have the luminance level, and this is, say, the histogram of the raw data. And what we're going to do is sum up the area up to some, I don't know, so we'll pick some luminance level, or pixel value. We'll find out the area under the curve up to this point, and then we multiply it by the max pixel value that we choose. And in the examples you see, it's like 100. That's what it is. And okay, so what's going on? The mathematical detail is that you set up an equation where you take your distribution and the uniform distribution, and you find some transform between these two. Yeah. Yeah. So that's the idea. That's what we're trying to do. So we're trying to sort of flatten our histogram. And this is what happens. So this is the original, the raw, and this is what happens when we do histogram equalization. So it really doesn't make a difference, at least from viewing the resulting histograms. All right, so here's a picture showing you the difference. This is the log image you saw before. And this is what happens when you apply just plain histogram equalization. So we wanted to do differences, and the way we do differences is that you could, now these are both normalized, you can simply say, okay, one minus the other. And now it makes sense. It makes sense in a way that you can explain to somebody and yourself. It doesn't make sense if you just have, don't take into account the image statistics. So another one thing I can say about this is that the histogram equalization is sort of like a, it's been around for a while. It's maybe even classical, and one of the sort of drawbacks of doing it is that if your data is noisy, histogram equalization will amplify noise. So I'll give you an example. Let's say we had, like, I don't know, faulty GPS signals here or something. Visually, we could identify them as noise. Maybe we could even take into account our service and say, we only accept GPS signals from trucks or something like that. If that was the case, then this would clearly be noise, and we could identify it by its spatial location, its neighborhood, or something like that. Say it's, you could identify it that way. But if we include it, if we don't smooth the data or denoise using a median filter or something like that, and then what happens is the heat map is we take the data, and the way we construct the heat map is we sort of like collapse it, right? So we lose the spatial component, and so now noise looks like anything else that, not noise, something here or here or here. So that's an explanation of why you should denoise your data before using this. Okay, well, that was about the heat map, and so we then take this heat map, this normalized heat map, and then we use it as a signal in our re-ranker for autocomplete, just to complete the story. So we also use it to a priori sort of like index our data. Actually, that's how we're architected. So you index the data beforehand, and then at runtime you re-rank. Okay, thank you.